Hey everyone, welcome to this video on set theory. Set theory is a fundamental branch of mathematics that deals with the study of a collection of objects. In this video, we'll explore the basics of set theory, including what sets are, how they are defined, and some common operations that can be performed on sets. We'll also cover important concepts such as power sets, metric spaces, openness, and boundedness, and we'll see how these concepts are used to solve various problems in mathematics and economics. By the end of this video, you should have a solid understanding of the fundamentals of set theory and be able to apply them in various contexts. All right, let's get started. So, as I said before, a set is a collection of objects, and this collection pays no attention to order. It could be a collection of numbers, or a collection of people, or a collection of anything. And it's really useful to formalize collections when it comes to economics because we often analyze decision making and resources that are best grouped in some sort of set. And when we're looking at a set, we have membership in the set that is defined by this symbol that looks like an E. So we say an element is a part of the set. And an example here is that 0 is a part of the set A, Harry is an element of the set B, and then Jack is not an element of set B with a strike through that element symbol. Some common sets that we'll look at in a lot of maths and economic contexts are natural numbers, which is defined as 1, 2, 3, all the way to infinity as integers. Sometimes people will use 0 in this set, and actually it's not really clearly defined in mathematics more broadly whether the natural numbers include 0 or not, which is, to me, kind of interesting that there's not a common consensus. So it's often useful to define which type of natural numbers you're using, and I will use natural numbers usually to define 1, 2, 3, and upwards. Integers, which is this z over here, that is equal to any integer, which includes 0, positive integers, and negative integers. We also have sets like the rational numbers, which is a fraction of integers, so long as it's not dividing by 0, and even numbers, where you can define the number as just 2 multiplied by an integer. Of course, there's several more sets than this, but these are some examples of common sets that we use. Pay attention to the empty set as well, which is equal to this circle with a strike through it, and that symbol is used to define a set that has no elements in it. It can be a bit of an abstract set to deal with, but is often used in proofs and in economic discussions. Okay, looking at some operators for sets, you have intersection, union, complement, and relative complement. And these are defined in the notation as these symbols here. And the formal definition of these operations are defined to the side here. So A intersect B is creating a new set where every element in this intersection means that X is a part of A and X is a part of B. That's the definition of this set. A or B, so A union B, means that X is a part of this set if X is in A or X is in B. A complement means that X is a part of the set so long as X is not in A. And then A relative complement B means that X is in A and X is not in B. These are the most common ones that you'll interact with. The definition of a subset, A subset B, if every element in A is also an element of B. A strict subset B, if this definition is true, and there exists an element in B such that B is not in A. So it's strictly a subset if there is some element in B that's not in A, but every element in A is in B. Okay, power sets. Power sets are defined as the set of all subsets of something. So the power set of A is equal to a set of sets, and every set in this set is a subset of A. So for example, the power set of A, which is 1, 2, 3 in this context, will be every possible subset, so the empty set, the set of 1, the set of 2, the set of 3, so on and so forth. These are all the subsets where every element in this set is also an element in this one. Notice that we have the empty set here because there aren't any elements in here, so the logical statement for all elements in this set, they belong to this one. There aren't any elements there, so it is true by default. Okay, and if the set has more than 3 elements in its inclusive, then the power set has 2 to the n elements. Lastly, cardinality is defined as the number of elements in a set. So for example, the cardinality of A in this case is equal to 3 because there are 3 elements here. Okay, that's the fundamentals and the basics of sets. And now let's start to build upon them to some important concepts about sets. Okay, metric spaces. I'm going to first start by explaining metric spaces more broadly and then hone in on the Euclidean metric that we use all of the time. So what is a metric space? First of all, let's just talk about a space. A space is a set endowed with some sort of structure, and that is to do with a function that is being used on a set. That's what a space is. And a metric space is a specific application of this where those functions have particular properties. So a metric space is performed on X, which is the set, and then the distance function D, and this distance function maps things from X to X to R. So X cross X to R, and this function specifically satisfies 3 properties for it to be a metric space. The first property is that the distance function on X and Y has to always have an output that's greater or equal to 0. And if the distance function is equal to 0, X must equal Y. Secondly, the distance function of X and Y must be equal to the distance function of Y and X. And this must be true for all elements. And then lastly, the distance function of X and Z must always be less than or equal to X and Y plus Y and Z in the distance function. And that's the triangle inequality. So written like that might seem a little strange and arbitrary, but this is actually establishing us to have important properties of a distance, Euclidean metric distance function, and then we can abstractly actually apply those properties to different types of relations that are being performed on the set. And if those relations are satisfying these concepts here of distance, at least in an abstract sense, it can also qualify as a metric space. So if we look at the Euclidean metric here, this is just the distance function where the function d that's operating on x and y is just calculating the distance between x and y. And that is done using Pythagoras' theorem here. And you can see that this is actually going to satisfy those 3 properties. In fact, this is where those 3 properties come from in a generalized way for a metric space. So of course the distance is always going to be greater or equal to 0 because you have squared numbers and then the square root of those squared numbers. And then if the distance is equal to 0, the square root must be equal to 0, and that can only happen if every input of x and y is exactly equal. The distance will always be the same for x to y and y to x, because when you square it, the order here doesn't matter of x minus y or y minus x. It's the same thing. And then the triangle inequality, which is the famous triangle inequality, will hold for distance. And I've got that written out here. The fastest way to go between 2 points, A to C, is in a straight line. And if you were to take a detour from A to B and then from B to C, that detour is always going to have greater distance than going directly from A to C. And then we have this less than or equal to, in the sense that if you lined it up, you could apply this definition from A to C somewhat more obscurely just by having the right variables in there. A to C and then C to C, for example. Yeah, so this triangle inequality is really useful, and often in microeconomics, actually you do it in macro as well, proofs on different things where you can use this relationship in terms of distance to simplify your expression with our triangle inequality here. Yeah, so that is this concept of a metric space. All right, moving on to some more concepts about sets. Ones that you would have hopefully seen before is this idea of openness. So a set can be open or a set can be closed. And to understand about a set being open and closed, you have to understand about different points and how those points relate to a set. So I've got 4 definitions here. An open ball is the set of all points that are within R units from X. And we define our open ball that is centered on X with radius R as the set of every point Y that is within R units of X. So you can kind of see how this follows on from above, where we're using our distance here and defining this set as all the points that are within the radius distance of our center X. And it's an open ball because it's strictly less than R. So it doesn't include the boundary when you're exactly R away from the point. And then we use this open ball to define our interior, exterior, and boundary points about a set. So an interior point of a set is defined like this. An interior point of S, a point is an interior point of S if there exists an open ball centered at X that is contained entirely in S. So you have a point, you can find an open ball with a radius as small as you like, where every point inside that open ball is also contained in S. And then that suggests that this point is definitely an interior point of S. A point is an exterior point of S if there exists an open ball centered X that is located entirely outside of S. So that these two are very similar, but for exterior point, you can find an open ball where every point inside that open ball is outside of S. And then a point is a boundary point of S if every open ball centered at X. It's cut off at the bottom here, but if every open ball centered at X contains at least one point in S and one point outside of S. So a boundary point definition is a bit different to interior and exterior because they have existence definition focused. There exists an open ball with blah, 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 blah. Whereas this one has a for all definition where every open ball has at least one point in the set and one point out of the set. I think this is best seen visually. So if we look here, you have examples of an exterior point here. So first of all, the set S is this circle that is shaded in, and exterior point here is very clearly exterior because when you draw this open ball around it, it's nowhere near S, and every point inside this open ball is not included in the set. An interior point here, this is proving the point is interior with our diagram because every point inside of this open ball is clearly contained inside of S. And then I have 2 examples of boundary points here. I might zoom in on them. Take a look at this boundary point first of all. This is harder to fully prove because the definition is every open ball. I've drawn 1, 2, 3, 4 open balls here. And in all 4 of those open balls, you can see that there are points included in those open balls that are out of the set. So that's these points over here on the side, as well as points in the set, which is actually to the right here. And in this particular example of a boundary point that is located on the boundary and in the set, actually they all contain a point in the set because this point at the center is in the set. But you'll always have points outside of the set no matter how small the radius of that open ball is. But you can still achieve this definition of the boundary on a point that's not in the set, where you have your dashed line. So these points aren't in the set, but this open ball centered here is always satisfying the definition where the open balls will contain points in and out of the set, no matter how small you shrink down the radius. So on this outside here, you have points that aren't in the set, and over here you have points that are in the set. And when you shrink the open ball down, that will always be true around that point centered there. Okay, great. And with our understanding of interior and exterior points, etc., we can then start to define sets as being open, closed, both, or neither. A set is open if all of the points in the set are interior points. Specifically, the set contains no boundary points. Although that's not logically true. but that is, I'll explain that in a second. And then a set is closed if it contains all of its boundary points. So if every boundary point that exists is in a set, it'll be closed. This is an example of a set that is neither open nor closed. It's not closed because this is a boundary point not in the set, and it's not open because this is a boundary point that is in the set. So this is an example of a set that's neither open nor closed. A set can be both open and closed if it doesn't have any boundary points. So it's true that all the points are interior, so it's open, but it's also true that it's closed because it contains its empty set of boundary points. The real number set, for example, is like this. There aren't any boundary points for the real numbers because it spans on forever. So it satisfies the definition of containing its empty set of boundary points. Okay, last thing that we're looking at in this video is the concept of boundedness. A set is bounded if there exists some real number k where the modulus of the point is always less than k for every point in the set. So you can think of it as being able to fit the size of the set into a metaphorical box, or actually metaphorical ball. And if you can do that for every point, then the set is bounded. And something like the real numbers is not bounded because you can't find a definitive value k to put all of the points inside a ball with radius k and have them fit inside, because you can always just extend on the real number line further outside of that box. And then a set is compact if it is both closed and bounded. This is particularly useful in a lot of theorems where we were looking at domains of functions that are compact, for example, and then as a result of that, plus maybe a few other properties, you get nice theorems coming out of it. And that adds in this idea of it being closed as well. Maybe something that you haven't seen before, if you're experienced with these topics, is the idea of upper bounds and lower bounds and supremums and infimums. So we can actually separate the idea of boundedness to being bounded above by something or being bounded below by something, as opposed to just being bounded overall. So a set is bounded above if there exists some bound b where every point in the set is less than b, e.g. 0, 1 in the real number line is bounded above by 2. Similarly, we have bounded below, where every point in the set is greater or equal to the lower bound b. And keep in mind we're looking at just one dimension here. The least upper bound of a set is called the supremum. So that is, if we look at our diagram here in our set of 0 to 1, any point on the real number line to the right of 1 is going to be an upper bound because the whole set is contained in the real number line beneath this number. And if we're looking for the supremum of the set, we're looking for the smallest upper bound. So the smallest upper bound is going to be this one here at exactly 1, where everything in this set is less than 1. But it is the smallest in the set of upper bounds. And likewise, you have the greatest lower bound as the infimum, because every number to the left of 0 is a lower bound, and then the greatest one of those lower bounds is 0, which is the infimum. All right, that's it. That is our crash course on sets. Hope you found this video useful and can use your more nuanced understanding of these properties of sets to your advantage in other theorems and contexts that require this nuanced understanding to do something. Hope you found it helpful. Thanks.